Hello again. I'm just going to continue on talking a little bit about ionic bonding to finish off this section of the PowerPoint. So, as we said before, ionic substances tend to be brittle, and the reason for this you can see in this diagram, that if you move a layer of ions, then what that causes is that you get ions of exactly the same charge next to one another, and they'll tend to repel each other, breaking up the crystal. That's why it's very easy to smash a crystal of salt if you have a big one, and it breaks up very easily. Having a look at more of physical properties of ionic compounds, we know that electrical conductivity varies depending on the phase that the ionic compound is in. Electrical conductivity is the ease with which an electric current can flow, and it depends on the degree to which you have charged particles free to move through a substance. Obviously, when they're solid, the ionic compounds hold their ions quite strongly, and so they can't move. So ionic solids, like a piece of salt, for example, are non-conductors. However, when they're molten or in solution, then the ions obviously can move. So under those conditions, if you could take a jar, your box of salt at home and melt it, then the melted material you had would be a conductor of electricity. And also, of course, when they go into a solution, then again the ions are free to move, and hence they conduct electricity. Let's have a look at that with a little bit more detail. So the solid ionic compounds, the ions are held strongly together in a fixed position, so they don't conduct. Molten ionic compounds or solutions, aqueous solutions, do conduct electricity. Solubility, if we're looking now at another physical property, solubility, that's the ease at which a solid can become dispersed through a liquid. Obviously, you must know these words: solute, referring to the solid that becomes dissolved, and the solvent is the liquid that does the dissolving. So you may have noticed that you can put salt into water and it dissolves readily, but if you put sodium chloride salt into oil, it doesn't dissolve. And solubility depends on the degree to which the solvent, that's the liquid, can attract ions from the solid or solute. And in order to do that, it has to have some kind of difference in polarity across the structure. Water, as you probably seen me draw on several occasions, is strongly polar. The two hydrogen atoms tend to be down one end and the oxygen up the other end, making a positive-negative dipole across the molecule, and so it can attract ions from the NaCl into solution. But oil, vegetable oil or other kinds of oils, are non-polar molecules, so by and large across the molecule there's very little difference in charge, so it can't attract the ions to either end of the molecule. And so to summarize then, these are things that would be worth writing down so that you make a note that you need to remember them. Ionic compounds have a high melting point. They are very brittle. Their electrical conductivity varies depending upon the state or phase, and their solubility will depend upon the solvent that they are being introduced to. So let's just have a quick look at the formation of ionic bonds. We already know about electronegativity. We dealt with that a little bit in the last topic. We need now to think about the extent of ionic character. So if we look at the electronegativity values, you can find a scale of electronegativity values on a periodic table in the data booklet. We use what's called the Pauling scale from Linus Pauling. They're dimensionless numbers, so no units associated with them. But if you have a look at the values of electronegativity, for example, down group 1, and then have a look at or compare them to the values in group 17. Group 18 isn't obviously on this periodic table. If you compare group 1 to group 17, you will see that you can get the biggest possible difference in electronegativity between a group 1 and a group 17, suggesting that, or indicating that, if you bond a group 1 metal with a group 17 non-metal, you will have the strongest ionic bonds, if you like. So this ionic character is the determinant of ionic bond formation, the difference in electronegativity between the partners. And if you have a difference of 1.8 units or more, then you can consider that compound to be ionic. Now, obviously, being ionic or being covalent is not a either or type of a thing. I know that we thought about this in probably year 11. You may have thought of it that way, but in fact it's always a continuum. So you can go from no difference in electronegativity up to values of 4 or so. But we put an arbitrary cutoff at about 1.8 units on the Pauling scale and say that anything more than that, it makes an ionic compound, and anything less than that, it starts to be a covalent compound. It will be a polar covalent compound if it's at 1.7 or 1.6, and it will be a very strongly covalent compound the smaller the number gets. And you can have a look at those couple of questions, or 3 questions to finish off, and be sure that you can answer these questions, because they're very typical of the sorts of questions that you might get in tests in the future, including your final exam. So make sure you can do that. That's all from me for the time being, and next time I will go on to look at covalent bonding in my next video. So all the best to you. Bye.